morning, everyone. Thank you very much for the introduction, Tim. My name is Mark Sprawson. I'm the Chief Commercial Officer here at EA Technology. I'm joined today by my colleague Tracy Pears, who is one of our senior consultants, and also by Emma Walker, who works in our external comms and marketing department. We're going to talk about a few areas that Tim's just hinted at, really, which are some of the great strides that have been made in the UK with regard to grid resilience, grid flexibility, and the integration of key new technologies such as electric vehicles to the low voltage grid in particular. I would just like to say, as we go through, all of these slides we're very happy to make available to everyone at the end of the session. There are some QR codes which are on some of the slides as we go through. If you could scan the QR code, basically that will enable you to then receive a full copy of the slides after and any other supporting materials. The QR code appears multiple times throughout. It's the same QR code. It's just to give you a few chances to scan it. You don't need to scan it each time it comes up. If I could also ask if there's questions as we go through, we will pause at the end of each section for questions. If you could put them in the chat, we will be monitoring that, and then we'll be able to come back to those at the appropriate time. So I look forward to seeing those as we go through. So today, we're going to talk about three key topics. We're going to talk about essentially what opportunities and challenges we've seen in the UK and how DSOs have been responding to those. And the three key areas we're going to look at is around grid edge intelligence. So how are DSOs in the UK using grid edge computing to drive real world benefits, both for their own operations and for their end customers? We're then going to link that into showing one of the particular use cases around how use of digital transformation and digital twins has enabled the UK to really accelerate with regard to the connection of low carbon technologies. Tim spoke in his introduction about the need to connect far more technologies to the grid to enable the challenge of decarbonisation. So we will look at that and look at some of the tools, techniques, processes that have been adopted and are now business as usual here in the UK that we think are world leading and really set the standard for where others will be following. And then finally, in the third section, we'll come on to talk about how do you take all this information, particularly from the information that's being gathered at the grid edge around the health and the condition of some assets that are there in the grid, as particularly the low voltage infrastructure becomes more and more crucial and critical to the delivery of net zero. How can we take data from some of these assets, which previously we've kind of been a bit fit and forget around this. We haven't always been monitoring them. How can we take that into our decision-making processes for prioritising our investment programme moving forward? So without further ado, I'm going to walk through the first two of these, and then my colleague Tracy will walk through the third, and we'll pause after each. So I'll start with the first, and again, there's the QR code for getting access to the slides. And the first is really looking at that grid edge intelligence piece. How are DSOs here in the UK using grid edge computing to drive real world benefits? And I think if we're going to talk about grid edge intelligence, we obviously need to talk about data. And one of the key questions that I often come across when speaking to DSOs around the world is whether we simply need to have greater amounts of data. Do we need to just gather more information about what's going on in the network? Or is it the case that we actually need to be smarter with the data that we're using, and we need to use it in a different way to drive decisions and drive actionable insights? And I think the answer to this is actually both, to a large extent. We do need greater amounts of data, particularly around the low voltage end of the network, but how we use that data and interpret it and actually drive real decision making from it needs to be much smarter. So I'll go on to explain a bit about that in the next few slides. When I talk about grid edge intelligence, some people tend to think, oh, isn't that just monitoring the network? So I'd just like to look at one slide here, which tries to draw out some of the differences between what we really mean by grid edge intelligence and basic low voltage monitoring of networks. And I think we're all very familiar with smart meters that are used ubiquitously now across many jurisdictions to gain some insight as to what's going on at the very end of the network, the endpoint. If you take smart meter data and maybe you stream that on a 30-minute basis, so you're gathering data points every 30 minutes, that comes down to around about 5 or 10 megabytes worth of data you might receive each day. That allows you to use that and make some sort of decisions off the back of it. When we're talking about grid edge intelligence, we're talking about much more high-performing computing devices that are installed at the distribution substation end of the grid. And what we see from that is usually these kind of devices collect data at around about 16 kilohertz, so 16,000 times per second, across all of the different circuits going out from that substation. And what that means on the left-hand side that you can see here is that actually in the UK, at each distribution substation where these devices are installed, we're collecting and processing around about 140 gigabytes of data each day. So that's around about 28 million times more data than comes from our smart metering fleet. But collecting all of that data isn't enough on its own. What do you actually do with that? And this is where the computing power comes in terms of running intelligence at the edge on the device and then only sending information back to the head end that's actually needed. So if you shared that data, as it says in the second bubble, on a 1 second data stream, you're still getting over a gigabyte worth of data from each device each day. This clearly will be difficult for comms bandwidth, for data warehousing, and so on. So what the clever bit of the grid edge intelligence really is to not just collect this data, process this data, it's then to pass that into something that is actually usable and is actionable by the DSO. So instead, what is sent is a stream of data with load data, alarms, events, key waveforms of incidents that are happening on the network, which turns out to be around about 25 to 50 megabytes per day. So it's only about 5 times more than the amount of data that comes from the smart meters, but it's processed in a way to make it immediately actionable. So that's the key thing around grid edge intelligence. So what sort of applications are there for this grid edge intelligence? And again, if we compare it with things like basic load monitoring, the real value of intelligence at the edge comes from being able to stack multiple use cases onto one device and one substation. So in the UK, we've already seen more than about 15 use cases for DSOs, and they span across multiple areas of the business. So I'll just show 4 quick examples here. Operations. So for field operations of networks, being able to understand in real time what is happening at the low voltage end of the network in a similar way to is done and has been done for many years at medium and high voltage through SCADA links. Generally, there isn't full SCADA implementation down to low voltage. So being able to understand what's happening, where the outages are, how you can respond to those outages, what kind of flexibility needs there might be on the network, all of these can be done within the operations group. There's then the asset management group, and this is really where it'll tie into some of the things that Tracy will talk about later around condition and the health of the assets as well. Being able to understand what sort of load cycles are being placed onto transformers. Are they experiencing short-term overloads, long-term overloads? Is this compromising the integrity of the oil or the insulating material within the transformer? Is it degrading and aging faster than it otherwise should? So there's the asset management play. There's then a network planning play, which is to improve capacity models and help really understand the growing demands on the network and how that needs to be invested in over the longer term. So looking at things like trends for load growth, looking at the amount of distributed generation export there is, the amount of what the voltage envelope is that we have to play in for each day as we get the voltage rise associated with the export of generation, and then the voltage drop associated with all the electric vehicle demand coming on in the evening with charging. And finally, connections, which again we'll come back to talk about a little bit later on, looking at things like harmonics data. Wouldn't it be great if you could use devices like this to actually capture harmonics up to the 100th, which is currently being trialled here in the UK, as opposed to having to deploy lots and lots of different pieces of equipment into one substation where each one of them could do one of these individual blocks. Being able to process all of this on one device is where grid edge intelligence really comes into its own. So just to make that point, what I'd like to say is that not everyone in the UK uses this in the same way. So we already see different DSOs come at this with different priorities. Some of them want to move faster in the operations area, some in the planning area, etc., etc. So I'm just going to bring out 3 use cases, the real use cases being used right now to show how that might play out. First use case that I'll talk through is around fault management. So very much an operations use case. So as it says on the slide, that the situation here is that fault management is a very expensive part of a DSO business, as I'm sure we'll all agree. There's much more regulatory scrutiny, there are penalties and performance targets around fault restoration. As I said, there has not been a lot of insights available automatically on outages before actually dispatching engineers to the field to try and effect that restoration. So what are we trying to achieve? We're trying to drive down the SAIDI and SAIFI. We're trying to improve that performance. And we're also crucially trying to reduce the amount of OPEX associated with the response to low voltage faults. And the simple diagram at the top right shows what I'm sure we're all familiar with, which is some nice sinusoidal waveforms. There's then a huge spike, in this case around about 7,000 amps, which causes the circuit to trip. And this is a waveform captured from the grid edge intelligent device. And you might say, great, how does that actually help me in my day-to-day? And I'll go on to show that in a second. Just before I do, I'd like to introduce a second use case. I'll then compare and contrast the two. So another operations use case is in the proactive fault management space. And this might be a bit more unfamiliar to some of you. It certainly was unfamiliar to everyone in the UK until just a few years ago. And this is really about saying, as we try and improve for all the reasons I said before about improving quality of supply, minimizing interruptions to customers, trying to offer the best level of service, particularly in an increasingly decarbonized world, how can we actually try and intervene before faults happen on the network? So to do that, we really need to have some knowledge and some insight onto the condition of those assets so we know which ones to intervene on and, crucially, where to intervene. And again, come back to this in a second. So what the diagram at the top of this slide shows is a similar signature, nice sinusoidal waveform again for the voltage, and a similar spike, which we're seeing in the current in the yellow waveform. However, in this case, last slide it was 7,000 amps and the circuit tripped. In this case, it's 700 amps. And what you see is it then goes back to having the nice waveform of the yellow showing the current going through there as well. There is no trip here that occurs. No one has gone off supply. Everything is still okay on that network. However, something happened to cause that spike. And what Grid Edge Intelligence can do is basically run clever algorithms on the device to enable you to identify how worried should you be about that spike. Is it because there is a fault that is developing and breakdown is happening in that cable joint or in that low voltage cable? So what we're seeing in the UK, again, is DSOs moving towards a pre-fault way of operating to try and actually fix faults before they happen and realize savings as a consequence. So how can you do this? So again, some example data here from some Grid Edge Intelligence. This data is taken from a fleet which is all installed in one geographic area. There are around about 700 substations there which are monitored, which equates to around about 4,000 low voltage circuits. And what is running on these devices is an application which allows the condition of the circuits to be evaluated. And what you can quickly see from this, from the pie chart, is that the vast majority of those low voltage circuits are in very good condition. So 3/4 of them are completely healthy. There are none of those little incidents that I showed on the previous slide being detected. We are not picking up pre-fault signatures. There are not faults that are developing there. You do not need to worry about these circuits. However, there are a smaller number of circuits shown by the red and the deep red, 2.3 and 4.9% there. So you're looking at around about 7.5% of the circuits which actually are expected to fail within the next year. So we classify these using the application again into failure imminent and failure likely. These algorithms have been trialed and tested over a number of years, and basically circuits have been allowed to run to failure to evaluate the accuracy of these algorithms. And what we now find with these algorithms is anything that is put into that failure imminent category, about 1/3 of the circuits that go into that category that are identified as being failure imminent fail within 1 month. And around about 2/3 fail within 6 months. So the algorithms are getting quite accurate at being able to say, this is a circuit which you need to intervene on. But that's only half of the problem, because just knowing that circuit is going to fail is not helpful unless you know exactly where on the circuit it is going to fail. So another thing that can be captured through these applications is then an impedance value. So basically it gives not just a likelihood of failure, but it also says the impedance value at which it is going to fail. And that impedance value can be equated into a distance from the substation along the circuit, pinpointing exactly where that location is. So how's that done in practice? So it's done like this. Again, DSOs increasingly are building low voltage digital twins of their networks. So here is a real example of a real UK DSO who has done this. And what I'm going to show here is just a 40-second video, which shows a load flow being run on this low voltage network. Running that load flow obviously means it is a full impedance model. So a piece of information has come out to the grid edge intelligence saying there is going to be a fault at 25 milliohms. So all the user does is types in there 25 milliohms and clicks locate fault. And 2 pins are instantly pulled up onto the map, showing exactly where that 25 milliohm point is. Because the network splits, it comes out from the substation shown on the right-hand side of this video. So you might think, okay, you've got two choices now, where do you go? And the answer is the system pulls up not just the location in terms of how far it is from the substation, but clearly it also pulls up how far it is from the closest joint. And hopefully you can see it says on the top one, 27 meters from the nearest joint, and on the bottom one, it's 42 centimeters. And experience has shown us, and I'm sure you will have seen similar, that over 90% of faults occur in joints, not in the main sections of cables. So the engineers go to the one which is closest to the joint. And indeed, in this case, it was that bottom pin, the southerly pin there, and the actual fault was in that joint. It was 0.4 meters from the identified location. And the DSO was able to go there, was able to repair that fault before it actually developed. So nowadays, what grid edge intelligence is driving in this operational sense is this kind of approach to LV fault management. Historically, cable replacement strategy and fault management was all replace when it fails. That's how it has been for decades. Now, that is still by far the majority. I'm not going to try and say that everyone is doing this and it is completely in business as usual everywhere. But there is more proactive repair going on based on data that is being gathered. And we know that all DSOs, as they plan for their next regulatory period moving forward, are putting together plans around having a much broader proactive repair team based on this condition data, with the intention to make that a larger portion of the overall budget as opposed to just the replacing on fault. And there are some DSOs across the UK that have tens and tens of engineers where it is their job now to do proactive repair rather than reactive. That's driving real world benefits. So by proactively repairing rather than waiting for failure, data we have from DSOs is that they're making around about a 40% saving in operational expenditure by managing those faults proactively. The other thing they're able to do, which again links into some of the things that Tracy will talk about later, is being able to target their interventions really more specifically. So there was one type of cable, for example, that is known to have lots of problems with it. And so a DSO had put together a case where they said, we need to go and actually replace all of this cable because it is a known defect, it's a known issue. And they came up with a plan to spend many tens of millions of pounds to replace all of those circuits. Rather than just do the replacement everywhere, what they then did was actually install the grid edge intelligence devices to monitor and look at the health of the cables. And what they found was, if you remember that pie chart that I showed you before, it wasn't quite as good as that pie chart, but there were still a lot of things in the green. So they were quite happy to leave those, continue to monitor them to see if anything develops, but actually target their intervention and their investment at those areas where they were the red and the amber colours. And what that meant was that they saved well over £10 million worth of planned investment by being able to instead monitor this. And the return they got on kind of how much it costs to deploy the grid edge intelligence and continue to monitor that versus doing the wide scale replacement was around a 40-to-1 benefit. So that's the operational use cases. I'll talk about one more use case in this section. And this is a use case which is more of a what is sometimes referred to as dynamic operating envelope. It's a use case that allows for greater hosting capacity of distributed energy resources, getting more things connected to the grid, being able to utilize the grid more effectively, being able to manage the benefits of flexibility at a very hyperlocal level. And the situation here, as it says, I'm sure we're all familiar with, is having more and more of these customer-side technologies connected is stressing the low voltage networks. And if you take a traditional planning approach to this, it can be quite conservative around what can be connected and how it can be managed. So thinking about how we can take a more proactive, flexible approach to this, what we want to be able to do is to gather real-time data, which allows us to use that data rather than model data for operational decision making. So really take that data, use it, bring that visibility to the fore, enable then customers to leverage their own assets and us to manage as DSOs that network more dynamically. That then means that it can be much more effectively utilized and means customers get more value from the assets that they've invested in. So I won't spend too long on this slide. There's a lot of detail on here, but as I said, you can get access to these later on. Essentially, as it says, you gather all the data at the very high frequency, generate the insights and the alarms. And in this case, what's shown on the top right is a profile, an envelope, if you like, of the maximum voltage and minimum voltage at one location. And this shows very clearly in real time where the limits are that can be played within to ensure that the network limits are respected at all times. So this allows for taking that, using that, communicating it out to customers in terms of flexibility signaling as to what's available, what's required at any given point. And by doing so, apologies, going a little bit quicker here, it has been shown to unlock around about 22% worth of additional network capacity versus the traditional approach, which was using modelled approaches instead of using the actual data from the field. So that clearly is enabling DSOs to utilise their network more effectively. It's enabling customers to drive more value from their own assets that they've invested in. It's a win-win for all concerned. So in conclusion for this section, do we need smarter or greater amounts of data? Well, what we really need is that higher granularity data to unlock the use cases that we then process at the edge of grid and send back the insights from that data rather than the raw data itself. So using a grid edge intelligence approach gives a scalable solution. It also means that one grid edge computing device in a substation, which can have multiple apps deployed to it over the air over its lifetime, can unlock additional functionality. So as I said, some DSOs might start on the planning use case and trying to unlock more planning capacity, but then they'll quickly add to that with the reliability use cases, with use cases around fault level management, power quality measurement, and so on, by simply deploying apps over the air. This is a rapidly maturing space, but it is already, through some of the examples I've shown today, delivering many millions worth of benefits, both to DSOs in terms of the OPEX savings, for example, but also to customers in terms of leveraging benefits from the assets that they've invested in. So I'll pause there, and the QR code's there again for you if you've got any, if you want to make sure you get copies of the slides. But any questions, Emma, from the chat?
So Peter has asked, does this system also work on LV overhead line networks?
Great question. So yes is the short answer. So the devices that we've seen in the field, and we have some, and there are other manufacturers who have some as well, are mostly geared around ground mount substations right now. But actually, we ourselves have a new product coming out in October, which is going up overhead lines onto pole mounted transformers, because we conducted a large scale innovation project with a UK DSO for around about 2 years, trialing that at pole mount to check that it will work and deliver the same benefits. So short answer is yes, most of what's been deployed to date is ground mounted, largely again because higher customer volumes usually in those ground mounted underground areas, but yes, it will all work at overhead networks as well. Brilliant. So I'll move on to the second section of the talk. Thank you very much for the question. Really to look at, okay, what can we do or what are UK DSOs doing right now to improve the connections process as we move to a fully decarbonised world? So it's not just about gathering data for operations purposes and so on, and for planning purposes that I've talked about. It's really about how can we, as DSOs, engage much more with customers. To do this, what you need to have is a digital twin of the network, like the one I showed on the very brief video before that was used for locating the faults. Once you've got that digital twin, it's very possible to, again, in a similar way, value stack and drive more benefit from that digital twin. So one of the main use cases for this is exposing some of this data to the outside world, to customers, for them to transform their connections journey. And the reason why this is needed is, again, really with necessity being the mother of invention. When we speak to DSOs, they tell us a very similar story all around the world. So this data is from the UK, but I've had similar data from Asia Pacific, from Europe, all around how connection volumes are really increasing rapidly. So if we go back a couple of years here from UK data, there was less than 350,000 annual requests for new connections to the network. Today, we've seen that increase by around about 55%, without really a commensurate increase in the number of staff available to deal with these applications. Going forward, and the reason I've chosen 2028 for this UK example is because that is when the current regulatory cycle ends and the new one begins, and everyone is currently planning for what they need for that new regulatory cycle. The message we've had from DSOs is that they're anticipating around about a 7-fold increase in connection requests for that period. So they're trying to plan and size their department and their delivery function for connection requests to deal with that level of increase. But how do you do that, short of employing 7 times the same number of humans to actually process these? What new systems, tools, processes can you maybe deploy as an alternative? So what we've seen now is that all of the DSOs in the UK listed on this slide on the right-hand side have basically chosen to not just go with the employ more humans approach, because that's not really scalable. It's difficult to find and to train those people. It's very expensive. What they've tried to do instead is to go for a technological-based solution to allow them to put more power into the hands of their external customers and really accelerate the whole connections journey. And what they've done by deploying such software solutions, I'll show a quick video in a second of what that looks like. They've basically allowed customers to self-serve their own connection requests and to take down the length of time needed for doing that from a few weeks down to just 9 minutes. So in 9 minutes now, customers generally across the UK are obtaining a price for their low voltage and in some cases medium voltage connection. So by enabling that and empowering customers, it cuts that time down from, as I said, several weeks to minutes, but it also unlocks the capacity of the existing workforce within the DSO. So rather than having to just try and process and churn through every single request, they can be focused on the higher value add type connections, the more complex connections that actually require that deep engineering experience and judgment, rather than the more simple, if I can call them this, connections that actually can be handled by a process. So what does that actually look like in practice? So I will show a very quick video, less than 3 minutes, of what this might look like. This is actually the very first system that went live. This is the simplest system. The newer systems that have gone live actually have got more functionality even than this in and make the user's life even more simple. But I like this video because it shows the entire end-to-end journey from a customer perspective. So here we see a customer going onto a DSO website, Northern Power Grid. They were the first DSO in the world to have this kind of a system. The customer simply goes down to, I'm going to apply for a connection. I would like to do this using their auto design tool. So the customer goes to auto design, and then what will come up is basically some legal text that explains the caveats and the limitations of the system, what sorts of connections you can apply for through here, what sort of connections you might need to contact the DSO directly around. Customer is happy to go through this process and use the auto design system. All they have to do is deliberately kept very, very simple for very simple connections. They have to just put the address of where the connection is going to be required. So here is an address, UK-based address. Are additional works required? So is there any additional upstream work on the MV? No. Is it a new house? Is it a commercial premise, a new EV charge point? It's a house. The questions tailor through. Is it electrically heated, gas heated, heat pump? Gas. Is there going to be an EV charger? Yes. How many houses is it you're building? 3. So this is a small infill development of 3 houses. It then calculates using Northern Power Grid's own design rules the amount of capacity required, 12.2 kVA. So all it's done is basically taken the decision-making process that was previously done via, algorithms and by simple measures to go through and encode that all in the system. It then brings up the map view. This is centered on the address that's been provided by the customer, and it features pre-populated LV network. Whenever the network, and this is the underground cables and overhead lines, whenever they are green, it means there is sufficient capacity within that network to make that connection, the 12.2 kVA it's being asked for. If it's red, there isn't. And if it's amber, basically it may be, but you need to speak to the DSO to find out more details. There's then user guidance to tell the user what to do. In this version of the tool, they have to just draw the site boundary of the site that they have and they've purchased, and then they simply connect in to the nearest asset. In the new versions, the connection happens automatically and it gives the lowest cost connection after looking at all options without the customer having to even do this. So there the customer's drawn their boundary, they're connected into a green cable across the street from that. This is all the customer has to do. Customer then sees again some more legal text and then says, here's your price, £20,500 plus taxes. They've received that in less than 3 minutes in this case, whereas previously they would have submitted that as a request to Northern Power Grid, would have waited probably a week for Northern Power Grid to process that request and get back to them. They then get their full PDF letter, which again they would have got dispatched to them from Northern Power Grid after the period of time when the engineer had studied it. It has the price in there. It has all the details for what they need to do next to basically progress with this connection. That's it. And the customer now has the price. Customer is happy because they get it so much more quickly. DSO is happy because no engineer has had to do anything there. So they've freed up engineer time and they've enabled their engineers to work on more higher value add, more complex matters. This can also be done at medium voltage, and it's important to note that on the slide I showed previously, which had the map on with the various DSOs, if you go onto UK Power Networks websites, UK Power Networks cover London and the southeast of England, they do this now at MV using this tool. And if the connection, it's more complex user interview because there's more to think about at MV, but it does do full backfeed analysis. It looks at N-1 running configurations for the network planners amongst you. Looks at how you can do that from a voltage, from a load, and from a fault level perspective, does full load assessment. If the connection that's requested is less than 1 MVA, and if the price comes out at less than €200,000, that connection is offered firm to the customer without an engineer at UK Power Networks ever looking at that. So the trust that has been built into these systems now has been adopted within these DSOs is very, very high. And they're happy to push through €200,000 connections without ever interrogating them or checking them. It's only when they go higher than that that they go past an engineer for a verification loop. So why was it that they had to do this? Well, as I explained previously, there was so many connections increasing and scaling that it was causing a real pinch point within their own processes. Another thing that they were finding, and again, I've seen this in other jurisdictions as well around the world, is that some customers will make multiple applications to try and find the best place to install one connection. So real world examples we see of this is electric vehicle charge point operators who want to put a public charge point somewhere on a city block, but they don't really care which of the 4 corners of the city block it goes onto, whether it's northeast corner, southwest corner, it doesn't matter to them. So what they would actually do is apply 4 times to the DSO for that same connection. And the DSO would have to do the assessment, come up with the price, knowing full well, and the EV charge point operator knows full well, they're only going to go for the one that is the cheapest and the fastest to connect. So what this does is enables the EV charge point operator to do that bit themselves. So they can look at those 4 options. As you saw from the video, it will take them less than 30 minutes to assess those 4 options. They can then just put in the application for the one that is the cheapest and the fastest to connect. So they're happier because they get to their answer quicker. The DSO is happier because that 75% of work that was otherwise abortive and wasted is now no longer necessary. They're only working on applications that are real, in inverted commas. And that's the second point, around 60 to 80% of applications, again, stats taken from speaking to about 12 different DSOs, don't get built. So that's wasted time for their engineers that could be more productively used. And again, the last point there, a quote I heard from one DSO was, I need to double my team in the next 2 years. That's just impractical from a cost management perspective and from a resource and skills perspective. So using these tools enable the much higher volume of work to be delivered with the same amount of staff. So if this is something that you're experiencing as well, we can happily share more information on this. There's an initiative happening across Europe, which is what the image on the right of the slide kind of hints at, called Connect Europe, Pan-European initiative, where we are looking to work with a number of leading DSOs, and we're giving them free trials of this solution to then participate in a knowledge share and to see how it could work for them. And if you're interested again in getting involved in that, please do just let us know via the links we'll send out if you send the QR codes back. So that's it from me. Any questions on that one?
We do. We have another question from Peter. Thank you.
Thank you.
So his question is, what about rooftop PV connections, and can voltage increase problems be predicted?
Yeah, absolutely. So the system, so I showed a really simple version of the system initially there. The new version of the system covers demand connections, it covers generation connections, it does a full load flow through it to look at the voltage rise and the voltage drop, and basically comes up with that voltage envelope. And then it colours the network in red, amber or green, depending not only on whether there's capacity in terms of the number of kVA, but also in terms of whether it would drive the network outside of those voltage tolerances. So yes, some networks, Northern Power Grid amongst them, who I showed on the video, they're using this for generation connections as well as demand right now. Great. Okay. Thank you. So I'll hand over to my colleague Tracy, who will take you through the third part of the presentation. Thanks, Tracy.
Good morning, everybody. So my name is Tracy, and I work in the asset investment management team at EA Technology. I've worked in this area for a good many years. So I'm going to talk you through, very briefly, high-level overview of our Invest software. So what is Invest? So it's our third generation web-based asset investment software. And so it started life, we've been working in this area for 25 years. And we started out using spreadsheet models, and they were bespoke for clients, generally UK electricity companies, and they predicted at current and future asset health. And we've developed this over the forthcoming years, and primarily with our clients, to introduce risk into the calculation, so that we could predict current and future, both asset health and risk. So now that we can do that, it enables us to prioritise and optimise investments and across all asset categories. So things like transformers, switchgear, cables, overhead lines, etc. So it's been developed for network operators, asset managers and engineers, primarily within the electricity sector, but we have also done deployments of this with slight modifications for the gas industry and airports and industrial sites. And the main difference is looking at the consequences in the case of asset failure, which can be different in the case of industrial sites. So the methodology itself, so the Invest methodology encompasses the key asset management activities. So things like, well, clearly asset data is key, condition data, and also performance, historic failures, etc. And often this data, the data sources can be disparate in lots of different places, not digitised, and depending on asset management maturity within an organisation, it varies between regions, which makes analytics and decision making not straightforward, not auditable, and can be different between regions and not repeatable either. So what Invest does, the methodology provides a framework to use all the available data in a consistent and repeatable way. It's a cyclical process as well, so improvements can be incorporated as the quality and availability of data improves. So it starts with asset data at the top, so that's clearly key. So things like what is the asset, how old is it, what's its operating conditions, etc. So there can be issues with at the start of the process with the quality of that data. So that needs to be have some sanity checks on the actual quality and accuracy of that data. We incorporate condition data, which can be visual condition and measurements, measured data points, look at historic performance, so failure rates, in order to be able to predict, to see what's been happening in the past and predict the likely performance going forwards. And the performance and condition of the assets means that we can then evaluate the risk depending on the consequences of the impact of what happens in the event of asset failure. And so, and then that enables analytics to look at trends, predict into the future, and inform the decision-making process of what asset interventions need to be done in order to ensure a reliable and resilient network. The process also, by carrying out this process, it highlights data gaps where clearly, if additional data will help to improve the quality of the outputs and give more granular results. So in terms of the actual real data that you would potentially use in a model, it varies depending on what the asset class is that's being modelled. But it always starts with asset definition data. So that's what is the asset, where is it, how old is it, what's its operating conditions, etc. So, and then that's enhanced by condition and inspection data. So that can be visual inspection data and also measured for transformers and switchgear. Partial discharge results are particularly useful. Oil analysis results for transformers as well, because these are good indicators of asset degradation and help to forecast when an asset should be intervened on. Policy is also incorporated, so strategic objectives of an organisation. So it helps to set the to align with investment targets when assets should be intervened on. And finally, the consultancy or the sense checking of the both the inputs and the outputs. So when you get the results, it's good to have the engineers and asset managers to sanity check the results, and they also help during the calibration and setting of the parameters, so that it is giving results that compare with the real life situation. So once we've got all that data and it goes into a model, the assets, in every case, assets are modelled on an asset by asset basis. So there's a lot of data and a lot of results that we can look at on an individual basis, asset basis. But particularly powerful are the graphical and matrix views. So we often present the results in a risk profile matrix, so generally a 5x4. So this is looking, so along the top you've got the assets are banded into health index bands from 1 to 5 and consequence bands from 1 to 4. So an HI1 asset is in good condition and low chance of failure, up to HI5, which is bad condition and high chance of failure. And an asset moves from HI1 to HI5 as it deteriorates. and the speed at which it moves along, it depends on various lots of things, but the condition and the operating conditions as well. And the consequences. So a C1 asset has low impact should it fails. So it might be a low cost asset and low impact on network performance, up to a C4, which has high impact, so high financial cost, high environmental consequences, or high impact on the network as well. So, and these are coded to show sort of relative importance on there. So the next slide shows some actual numbers of populated from an actual client. So you can see on there there's just over around 500,000 assets in this population, and 263 of them are classed as or have been identified as high probability of failure with high consequence. So they're the important assets in terms of getting them off the system, and they should be planned for proactive replacement. The next, so an HI5C3, they're also important assets that clearly and should also be planned to intervene and remove from the network. Then the high health ones, so in the C1 and C2 bands, that their removal tends to depend on corporate objectives and appetite for risk within an organisation as to when you would do those. The HI3 and HI4 asset blocks, they should be planned for their future investments. And this profile is done in the current year. So by running the model forwards, you'll be able to see how quickly the assets are moving from the HI3 and HI4 and plan accordingly before they get to HI5. The HI1 and HI2 assets, they're all in good condition, and nothing needs to be done in the short term on those at all. So those risk matrices help us to prioritise the asset interventions based on the condition and risk with the assets, and this provides different benefits for different stakeholders. So for regulators, it supports transparency and alignment with regulatory expectations. For network operators, it provides the best practice framework for predicting health and risk of assets, and can justify investment decisions using a structured framework. And for customers, the benefits include contributions to improved reliability and safety of the assets and the network, ensures efficient use of customer funds, and promotes accountability by linking decisions to measurable outcomes. We've been using this methodology, as I say, in various evolutions from around the early 2000s, and we've used it with over 70 utilities globally now. So just a couple of very quick case studies. So for the GB DSOs, so in 2015, the GB regulator, Ofgem, introduced regulatory reporting requirements and required that the DSOs jointly developed a common methodology for regulatory reporting. So that they did this with ourselves, and the unified and common methodology that has been come up with, and is agreed by the regulator is based on our invest methodology. So it's standardised in that it has uniform and standardised inputs and calibration values, which can't be changed by the users. This is all publicly available as well. The methodology, it's published on the Ofgem website. So, as I say, the methodology is common and has to be used by all of the GB licence holders, and 13 of 14 of them are using our common methodology models in Invest. So, and that's to put some numbers on it. So that's equates to just under 3/4 of the asset spend is governed by the common methodology, which equates to £3.3 billion in the current price control period, which runs to 2028. So at the moment, preparations being made for the next price control, and the asset groups that are going to be included are being expanded, so that percentage spend and value will increase from 2028. A second case study is we've worked on a trial project with HEP ODS in Croatia. So that's the national energy company in Croatia. And then their challenge was regional autonomy. So it's divided into a number of regions, and the data and the policies are not consistent, or were not consistent between the regions, making it hard to plan on a national level. So we worked with HEP and EIHP, held a series of workshops, three in total, to look at what the data availability was, and we built standard asset models for them, using data from 2 of the regions that had the best data. So that was transformers, switchgear and cables. And we also did an overarching model for the substation to include the transformer and switchgear assets, showing where the investments needed to be made. So, and the outcome of that, they now have an increased understanding of asset management techniques, and a transparent method that they can use across all the regions and roll out to other asset groups as well. So finally, I've just got a few screenshots actually from the Invest software. So as I said, this is the 3rd generation. It's web-based, mainly graphical, and it's very intuitive to use as well. So this screenshot is showing a map view with the assets displayed on it. So they're displayed as a series of donuts, which are showing with the number of assets, and that's representative of the size of the donuts, and the colours. I don't know how well you can see it. So it's red, amber, green, showing the proportion of assets that are in good condition and bad condition, medium condition. So on the right, on the left-hand side, there's summary information showing how many assets are displayed on the map, what the number of bad and poor assets, and the risk associated, which is just disappearing off the bottom of the slide. There's also filters above that, so that different or more or less data can be displayed at any one time. So for example, by asset category, by organisation, if that's applicable, by region, and those filters are configurable at start of a deployment. So it's then possible to, by clicking on any of the donuts, drill down to a far more granular level. This is showing primarily different pole lines, and with some switchgear assets on there as well. And the other thing to note is that at the top left-hand corner of the screen, so there's a slider, so it's possible to see what's happening to the assets from the current time over time by pulling the slider across to the right, see how they change colour or not change colour over time, depending on what condition they're in. And then drilling down again by clicking on an individual asset, you get a map view of identifying where the asset is. And on the left-hand side of this is the what we call the methodology view. So it's showing how the methodology, I thought, is broken down and various factors. I don't know how well it's showing, and you can see that, but it's got the values for how old the asset is, what the duty and where it is, and condition factors and consequences in the different categories. And from here as well, so if the observed condition, for example, is bad, it's possible from this screen to actually interrogate the model itself. So you can look at the inputs associated with this particular asset and see why the factors have come out as they have. That's very, very powerful and quick and easy to interrogate. And finally, so there are different dashboards. Dashboards are configurable to display what is of most use to an individual user. So this one here on the 4 tiles, so it's showing the health index now for 2 different asset groups for the different colours. The top right is the risk in the different risk categories that we've got, again, for the 2 different asset categories. The bottom left is showing the risk matrix, the one I talked about earlier, and then the final one is showing how long there is to what we call end of life, so when it should be being investigated and replaced. So that's in summary, that's a quick summary of the software and the methodology. So it's transparent and importantly, it's configurable. So to align with corporate objectives, it operates with minimal data. So if we can actually get results from, as long as there's an asset identifier and an age, there will be a result. And then when more data becomes available, then it improves the granularity of the results. And from those results, it identifies where investments should be targeted. Any questions?
We do have some questions. Peter, thank you so much for sharing those questions. Some of them require a longer answer, and in the interest of time, I'm just going to ask one. But if you wouldn't mind dropping your email, I can get a longer answer to you on the other bits that you asked. One of Peter's questions was around how Ofgem utilise this system. He says that he saw the introduction of the health-based methodology back in 2010, but he hadn't seen the risk matrix before. Is a health index score and the other matrices that we use, is it still utilised by DSOs to convince Ofgem of investments?
Yes, very much so. The regulatory settlements are based on the risk matrix now with no intervention, and then the risk matrix following the interventions. So I was showing them with the matrices with the numbers of assets, but you can assign a value, so that will show the risk associated with each of those cells. And then in the Ofgem is very interested in the delta, the risk delta. So when you've got the matrix after you've done your interventions, it's all to do with the difference between the risk with it after you've intervened compared with no intervention. So yes.
So thanks very much, Tracy. So my final slide to conclude, and I'll hand back to Tim and Christy. Thank you all for your engagement, for the questions. So we've tried to cover a few different areas here today that span the spectrum really of some of the activities going on with DSOs, particularly around kind of digitalisation, transformation, how they're making their grids more resilient, and how they're embracing new technology and the use of flexible resources. Talked about grid edge intelligence, how that's empowering DSOs to manage their costs, to improve reliability, and to unlock that flexibility, and some of the real world benefits and use cases that are currently being deployed in BAU. We talked about some of the connections approaches and how it's allowing for faster, smarter and scalable connections. So not just about increasing the size of the team, which is not a scalable solution, but using better technology and process to actually unlock that and to put the power in the hands of the customer as well. And then Tracy walked through how you can then use all that data, and increasingly more and more data now is coming from the LV side of the network as well to go into those models that Tracy showed, because again, previously there was just no data available. The grid edge intelligence and the being able to use those apps to identify the health of those assets is starting to revolutionise the way in which the investment planning decisions around those assets are now being made as we head into the next regulatory period here in the UK. So hopefully that's enabled you to kind of see some of the challenges that there are, but some of the great opportunities that exist to try and meet those and deliver world best performance for networks in a smarter, decarbonised future. So I'll hand back with that to Tim and Christy. Thanks very much.
Thank you, Mark and Tracy and Emma. Emma has actually just shared the slides or linked the slides in the chat. Thank you very much for that. I think we will share the presentations as well, and with your contact details, if that's okay, so that people can follow up with you separately if they would like to. So we're absolutely bang on time, which is great, and happy now to move on to our second presenter, which is Kraken Technologies. This is a different angle on grid flex. Actually, Kraken specialize in intelligent management of EVs and other flexible grid resources. They have 6 gigawatts under management. Sounds a bit like a hedge fund. So with no further delay, let's move over to Kraken. I'm not sure who is online from Kraken. We know Pete Noyce, but perhaps it's one of his colleagues. Would you like to introduce yourselves, Kraken Technologies? Thank you.
Thanks, Tim. Can you see me and hear me okay?
Can hear you fine, but can't. Now we can see you. Yes, excellent. Yeah. Hi, Pete.
Yeah. Hi. Good morning.
Thank you.
Thanks for the introduction. You've got the pleasure, I hope, of having 3 of us on the call today. So there's me. I'm a senior lead in the regs and markets team in Kraken. We've got I'm based in the UK. We've got Jack Greenwood. He's a product manager based in the UK. And also Yannick, who is a senior solutions consultant based in Berlin. So you will hear from each of us. I'm just going to load up the presentation because I'm going to do a bit of scene setting for us. Okay. Please can you let me know when you see that? Yeah.
Yes,
okay.
All good.
Okay, lovely stuff. Okay, so yeah, I'm going to start off by doing a bit of scene setting. To explain a bit about the world we inhabit, the world that we see around us, and some of the challenges and opportunities that we're looking to tackle. What world are we operating in? Well, I think we can see, or we perceive, that there is the start, at least, if not the early stages, mid to early stages of an energy transition happening in Europe. And I think that should be hopefully clear and apparent to everyone on the call, there are ambitious renewables targets across Europe. There are ambitious emissions reductions targets. There are ambitious, there is ambitious legislation that is trying to grow the amount of renewables and evolve the way in which we see electricity and, for example, grow the flexibility of the systems across Europe. We also see the growth of distributed energy resources like EVs. So if we have a quick look at some of the countries of interest on the call today, we can see that's certainly the case. If we just look at a snapshot of EV sales, we can see that's certainly the case across those countries. So blue is battery EVs and green is plug-in hybrids. And there's a definite trend towards growth in sales of these vehicles in the past few years. From the latest available figures that we could get, we can also see that there are some ambitious renewables growth targets in final consumption across some of the countries again on the call today. So there's change happening on the ground. There's even more change likely because of some of the targets and legislation coming in, and that puts us in a position where we are really seeing big amounts of change, and that brings opportunities but also some challenges. So we know that there have been issues, very public issues across Europe, particularly the example of Spain earlier this year. And we know that investigations are still ongoing into the exact causes, but it's clear that this energy transition has, like I say, brings opportunities but also some challenges, and that will require new ways of thinking about how energy is produced and consumed, but also about how the energy sector as a whole is managed, and that we need to change how we think about that so that we can mitigate some of the political, economic and operational risks that this transition represents. One way that we can meet those challenges is, of course, by increasing network build. So if we think about some of the example headlines on the previous slides about constraints in the UK, increasing the amount of network that we have available, particularly to shift to the changing supply and capacity mix, is of course important. But we will absolutely also require a shift, an increase in the flexibility of supply and demand dynamics in order to modernize and to meet the shifting habits and the growing electrification and the shifting supply mix that there is there. And Flex is going to play an increasingly important role. It can mitigate against the impact of grid build delays. So even if we want to use grids to mitigate a lot of the risks that we see, there are of course risks of grid build delays. Supply chains are in lots of cases reliable, but some of the materials can be quite hard to come by, particularly when everyone's trying to build at the same time. Flex can minimize the grid build needed at all by maximizing utilization of existing network, so shifting demand across and reducing peaks. We can better utilize the network that's available already. And Flex is also going to be really important to improve the operability as we move towards a more intermittent world. And what we'll need is Flex in all its forms. So having, not relying on just one kind of Flex, for example, battery storage. If we don't rely just on one type of Flex, we're spreading our risk. We're also creating competition, which helps ensure value for money. We're better addressing the different needs of the grid, because different types of Flex might excel at particular needs. And we're also reflecting the different sectoral and cultural differences out there on the demand side. So people will respond differently to different incentives. We're going to need a bit of everything, basically. And that means fast-acting flex. So, of course, battery storage, longer duration storage, but also demand response in its many forms. So explicit procurement of flexibility, implicit operation of flexible devices. So devices in the home or workplace that respond to price signals may not be selling explicitly to flexibility markets. We need automated, but potentially also manual. So we've seen massive success of manual demand response schemes in the UK, where people receive signals with good warning. Look, we want you to turn down, we would love you to turn down your demand in this period, and here's a small reward for doing so. We've seen massive uptake of those kinds of schemes. So I think each is going to have a role. And the good news is that Kraken supports all these kinds of flex. We are already part of that energy transition. We already have a significant amount of BESS on our platform that is using our platform. We'll hear a bit more about that later. We'll also hear a bit more later about the demand response that's on our platform and how we're supporting that, and what the uses that we're supporting it for. The key thing here is we are already managing massive capacity, amounts of capacity. This is a proven solution. It's something that is happening, and it's happening now, and not just in the UK. So very quickly, what is Kraken? It's an end-to-end operating system. So it's built up of lots of different products that I think each assist in different bits of the energy transition, right the way from supply through to demand. We're going to focus mainly on flex today, primarily because of the content of the first presentation that you've had. I also think it would be particularly relevant for a lot of the people on the call. But if you want to hear more about any of these, just reach out to us. I'm going to very quickly dive into one of our biggest products, which is Kraken Customer. This is an operating system for energy suppliers. We've got lots and lots of big suppliers that are using this system already, not just in the electricity sector, also in water and broadband sectors. There's more than 60 million accounts on our platform. And what it's really doing is bringing legacy systems into one place, bringing data into one place that is modernizing how utilities respond to the energy needs of their consumers and how they engage with those consumers. And this, together with the other parts of the platform, is powering a lot of the stuff that you're about to hear about on Flex. So they kind of work hand in hand. They can be used separately, but lots of institutions are starting to use the customer product with Flex product. But as I say, they can be used separately too. So I'm going to hand over. That was a bit of an introduction to Kraken. Please do stop us at any point with questions, but we'll also have time for questions hopefully at the end of the presentation. But I'm going to hand over to Jack, who's going to talk to you more about part of our Flex product.
Great. Thanks, Pete. Thanks, Tim. Hi, everyone. I'm Jack, as Pete said, also at Kraken. So I've been with the business a few years now, and I'm one of the product managers. So working with customers in order to get the right bits of software to the market that's going to help address some of these challenges that Pete outlined. And what I'm going to do today is talk to you about a specific bit of software that looks to target large-scale assets and large-scale flexibility. So most of that portfolio that we would put within this product is grid-scale storage batteries, but it's not limited to that. So a lot of what I'm talking about can be used with renewable assets or with other flexible forms of generation. So that could be CHPs, gas assets, hydro, things like that. So I'll get you to jump forward to the next slide now, Pete. So these are the three sort of key topics that I want to talk through today. So Pete gave a really good scene setter around the changing system. So I want to sort of go into a little bit more detail around what these changes are and what this means in terms of market dynamics and what that means in terms of the assets and types of software solutions that will be required in the future. So that's the first point there. The system is changing, and that's what we want to talk about. The second point is, once we've understood the change in the system and what that means, what's the opportunity there for yourselves as participants in that market to monetize that flexibility that Pete was talking about? So this could be energy storage or other forms of flexibility. And then the third point is, how can technology help you with that? Not just Kraken, but general technology. What is the problem that we think energy tech fills that gap for? So without further ado, I'll jump into that first point, and maybe the next one as well. So what we've got here on this slide is a view of various different types of technology. So this isn't to say that these types of tech are going to be what makes up every grid in the future, but we have seen the case that it's becoming more economical to build renewables, conventional renewables being solar and wind, as well as battery storage technology, while a lot of the baseload and conventional peaking technology is remaining quite flat in terms of the cost. And what that means is we're seeing a lot of grids that are moving towards either more balanced mixes with a lot of that baseload and conventional generation, as well as some renewables and storage, or we're seeing grids that are pushing really fast into those cheaper forms of generation and storage, and looking to really push the envelope in what can be done with renewables and flexibility. Next slide, please, Pete. And what that means for grids and for stability, we're starting to see the challenges of that. So as we see synchronous generation decrease and non-synchronous generation increase, so non-synchronous generation, I'm of course talking about inverter-based technologies being solar and wind, synchronous generators being turbine-based generation, so gas, coal, nuclear, things like that. We're seeing almost reaching 50% at different points in different grids. So this plot here is of the national grid in Great Britain. And we can see in 2022, there was a point when synchronous and non-synchronous generation was equal, and it sort of rebounded a little bit. But this presents significant challenges for system operators as well as participants in the market. Challenges around inertia, around frequency control, around voltage control, all sorts of things we've seen before in the European market, and we're seeing recently with the build out of renewables in various different markets on the European continent. Next slide, please, Pete. So this is one reason why energy storage and flexibility and batteries are useful within the grid. So that is to support the build out of renewables. All those challenges that I just mentioned, so that being inertia, frequency response, voltage control, reactive power, things like that, can be supported by storage, by flexibility, and particularly by batteries. But that's not the only change we're seeing, and it's not the only reason to look at batteries and energy storage. Let's go to the next slide, Pete. What we're displaying here is a representation of a traditional household demand profile. And that's something that we've seen basically since power grids began. So on the left, we've got the overnight period. Then as people wake up, sort of comes up to a fairly steady daytime profile. Then in the evening, we have our evening peak, and then people head to bed, and that sort of trails off. But what we're seeing now with distributed energy, but also with transmission connected or distribution connected generation, as well as storage, Pete, jump to the next one. We see that with solar, we're getting this cutout in the middle of the day. So the demand profile is changing, as well as the supply stack on the other side that's providing that. And we're seeing in the middle of the day, less demand, as well as an influx of cheap supply, which really changes the game in terms of what these demand shapes look like. Next slide again, Pete. As we move into more electrification as well, we're seeing increased heating and cooling demands in the morning and the evening. And then final slide for this one, as well as like Pete showed at the very beginning, increased EV sales is putting a bigger strain on the grid. That being people coming home from work, plugging their EV in at their home, and we're seeing this big spike in charging. And so, I said final slide, but now on this slide. And so we've gone from this conventional, quite predictable at scale, household demand profile and operational demand profile, to a really complex and choppy one that it presents challenges for the grids of the past, for conventional baseload generation, and it also presents challenges for the new types of generation, so for renewables and things like that. All things that I'm sure you're very aware of. So we can jump through the next slide and talk about what Kraken sees as the opportunity here. So adding energy storage enables us to cope with that new shape in terms of time shifting the power, but also any of the secondary issues that come along with a choppy demand profile like that we've already mentioned. So voltage, frequency, things like that, managing the grid. So that comes to the end of point one, sort of setting the scene around the system and the changing power grid. And we've talked about why we think energy storage and batteries and flexibility is going to be quite useful. So the first one being supporting renewables and supporting the build out of this cheap zero marginal cost generation. And the second being supporting the system to deal with this new changing demand profile. So next slide now, Pete. Let's talk a little bit about the opportunity for yourselves as market participants moving into the flexibility and storage space. One more slide. And what we see in Europe and generally globally is there can be two markets for flexibility and energy storage, and those being ancillary services, so services designed to support the safe operation of the grid, as well as wholesale markets. Conventionally, these are day-ahead or intraday markets where storage can create value through arbitraging the wholesale price, either across markets or within one market across time. Next slide, please, Pete. And what we see in Europe is that there's significant value in not only these batteries being a time shifter, so arbitraging the market and buying electricity at one point of the day and selling it another, but providing services to the grid. And so what we have here is an example of FCR, frequency containment reserve, in Germany specifically, and the prices of that as we move through its life as a market service. And we can see there's significant value there and varying value as more batteries come onto the system. And that leads me to the next point. Next slide, please, Pete. So these types of services, as more batteries come onto the grid, they saturate. And we see that the price that could be very high, so in the case of Germany, hasn't yet saturated, can really fall quite low. And so generally people looking to monetize these assets, to take advantage of the opportunity to support the grid in a way, will initially start with quite a simple job, which is use that asset to support the grid in frequency services and voltage services and balancing services like that. But as those services saturate, they're no longer compensated effectively for that service they provide. Next slide, Pete. So despite this, we also see that within wholesale markets, what we're showing here is plots of or distributions of wholesale market spreads. And on the bottom in green, we see the prevalence of renewables in each of the grids that we're looking at. So on the left, we see 43% renewable penetration with a relatively small distribution of prices within the day-ahead market. And as we see this increasing, we see significant increases in the width of that distribution. And this is something that we've that Kraken has, but also wider market participants have studied and seen has to be the case in a significant manner. That as renewables increase, we see the spreads in the wholesale market increasing too. Next slide, please, Pete. So that leads us to a question. We've got this this grid that's changing and needs support. We have various ways to monetize these assets that are going to support the grid. So that being frequency services, voltage services, reactive power services, as well as wholesale markets. So what role does technology play? What role does software play in this environment that we find ourselves in? So if we jump through to the next slide, Pete, we see that again, I'm looking at Germany as a case study and looking at recent months here of a battery index in Germany, and we're seeing if we split the revenue that this asset could have made, there's a fairly even split between FCR, AFRR capacity, AFRR energy, as well as intraday trading and wholesale markets. And this is sort of a key point I want to drive home with these flexible assets in the market, is that the key or the best traders and the people that are able to most effectively monetize these assets are trading across multiple markets. So that chart I showed earlier, where we had a price plot of a frequency market, FCR. Initially, when batteries first enter a market, traders are able to enter a significant portion of their volume into a single market. And because there are no competing assets, they're able to achieve good returns. But as these markets saturate, we see that the best traders derive revenue across multiple markets. So we jump through to the next slide. I think we've got a good example of that. So in Great Britain, one of the more mature battery markets, we see that there are a lot of different trading strategies, a lot of different assets. And for the vast majority of assets, traders are still stuck in the old way of trading, which is primarily ancillary services, and then a small amount of wholesale trading or cross-market trading. And we see that gets them reasonable returns. But when we look at the best traders and the people that are really at the top of those leaderboards, at the top of the index, we see that they're still leveraging ancillary services in a major way, but they're also looking at complex cross-market strategies, trading in the wholesale market, and looking to monetize the assets in that way. So it's really critical that when we're in this environment where the grid needs support, we need to be looking at how we can support the build out of renewables, support the grid as these renewables make the grid slightly less stable, that we leverage software to make sure that these assets are appropriately compensated for the service they provide. Just a question there. That's a really interesting question. I'm actually not sure if we've seen the grid effect, but generally, what these traders are rewarded for is for alleviating constraints, is for providing support in terms of frequency, voltage, reactive power markets, as well as physically shifting the electricity in the system. So if we say the wholesale arbitrage component is these assets being paid for storing the energy and providing it at times when it's needed more, and then the ancillary service. So I think the ancillary services are rewarded for supporting the grid, but then the energy trading is supported for physically arbitraging these things. I think arbitrage, depending on the market, may if there's location or price signals, but maybe that's a discussion for another time, or we can take that up towards the end, because I think this is a good line of questioning. Maybe next slide, Pete, and we can close off this section. So what we can see is that revenues at various different markets within Europe very significantly, but we can see in different regions at different periods. So I believe this is 2023. We see significant revenues from this type of trading, leveraging advanced software. And I'll go to the final slide before I hand it over to Yannick. And I wanted to talk, just summarize what I've talked through today. So first point being why we need energy storage. So that's what we talked about first. Renewables coming in as zero marginal cost generation and putting pressure on the system, as well as a changing demand profile. These storage assets are able to help support that and then and create a more resilient system. The second point is once these assets, or once we've explored this environment we're in, what is the business case to build these assets? And we see it's a combination of ancillary services as well as trading in the wholesale market. And then what do we see as the secret to success? It's that cross-market trading. It's looking to monetize the asset in as many ways as possible. And I think something that's worth pointing out with this, when we talk about the software, this is sort of the key part of Kraken as a software provider in this particular product line. So we offer the control of these assets, as well as alerting on the performance of these assets and the optimization and support of trading around these assets. So that includes trading across these multiple markets, being frequency, voltage, reactive power, as well as supporting the arbitrage trading, as well as providing all of the data around these assets to asset owners as well as utilities. So I'll pause there, and I think Yannick is going to talk through more of the demand response. Pete, did you know if we were planning on doing questions sort of halfway through or at the end?
Well, I think I said at the start we can do them as we go along, which you have, but we've also got some time at the end to take questions. So maybe should we move to Yannick and then we can do questions at the end if we've got more that you haven't addressed?
I think we're probably okay. I think it was the question around arbitrage and the effect on the grid, which I think Yannick had some thoughts on as well. But I think we got maybe 80% of the way there. But Yannick, I'm not sure if you wanted to address that yourself and then jump into your section.
Yeah, of course. So happy to briefly add some thoughts on the question, and then happy to take that towards the end in more detail if you like. So I think overall, yes, arbitrage trading can potentially cause increase in congestion as long as there are no locational price signals. And that is in most markets in Europe really not the case. So you have like nodal pricing or some of these things in the US. However, in Europe, not really prevalent. This is more so the case in some markets and in others. So a market where this might occur is Germany because it has a single price zone. But for example, this might occur just a bit less in Italy because you have, I think, 7 different market prices. So there are like some parts to this in Europe. So yes, it might cause that, but it doesn't have to. And I think the other part, if I got your question correctly, where the trading of on ancillary markets, what that does and how these things interact. So yes, there is of course an effect, and the more you trade on ancillary markets, the less availability you have to, for example, trade on the day ahead, because gate closure on, for example, the primary reserve happens like in most markets ahead of like before the day ahead. So the attractiveness of these markets and how beneficial what your battery does is to the grid or not does depend on the individual market design. Cool. Then let me maybe move on with the take on residential flex. So as Jack already mentioned, there's a lot of things changing in the system. And so we're going to look at the chart on the left. This is pretty much what Jack already mentioned. So the demand profile of households is changing mainly as a result from your appliances. So you have AC, which is air conditioning coming in, or generally heat pumps or heating and ventilation in any form. It's just these appliances are gaining more and more traction in Europe, and this will do something to household profiles. You will have residential solar, lowering the demand during the day. And then in the evening, you have your typical assumption of people come home, plug in their EV after work, and it just starts charging. In the prior part of the presentation, the main thing we've talked about is what can you do if all of this just happens and you have to fix it on a grid level. So this is where utility scale batteries come in and sort of bigger market design questions. However, what I'm going to talk about now is, can we also work on the residential level to maybe make this impact a bit less severe? Because the more we can make demand, and in this case household demand, but of course also potentially commercial and industrial, make do what is beneficial for the grid, the better this is for everybody. So the less, for example, say peaky or like the less extreme demand profiles are going to be, the less of a strain this will put on the grid. And this is what we then see on the right-hand side. And this is where Kraken's, what we call a residential flex offering, comes in. So in a nutshell, what this piece of software allows our clients to do is that our clients are usually, for example, like suppliers. They can smartly manage their household's appliances if the household allows them to do so. So this, for example, allows the supplier to decide in which hours, on which periods of time to charge a consumer's EV. So the consumer just tells them, hey, I want my EV fully charged by 7 a.m. And the supplier then, for example, gets the right to not charge that when the household plugs it in at 7 p.m. in the evening when it's expensive, but for example, to charge at midnight or 4 a.m. when there's maybe wind blowing, demand is low, you have low prices. It's better for everybody. And you can do that with all of the appliances that I mentioned before. And in an ideal world, that gets you to something of a profile that you see here on the right. So again, you have the traditional household demand curve as the white line, but then even with all of the appliances, if you're able to flex the devices that I talked about, this sort of gets you to the purple dashed line that is even smoother than what we have right now. So there's huge chances in being in the ability to shift demand just on a wider level. This has upsides for, I'd like to claim, almost everybody involved. However, given the audience and the topic of this meeting, I will mainly spend my time talking about benefits to the grid, and I'm going to do that based on two case studies. One is from the British market, one's from the German market, where we've talked to some of our trusted partners and we've started flexing household demand for the benefit of the grid. So the first example, which is on the next slide, we're going to take a look at the British market. Don't worry, I know it's a cramped chart. I'll walk you through it. So what we did here is we talked to one of our partners on the distribution level, and we looked at how we can shift household demand. So very important, the household needs flexible or smart devices to avoid grid congestion. And to make sure our technology actually works, we put all of the clients who are willing to participate in one of two groups. So in the upper part, you have the control group. So that is what they would call status quo. So they still have flexible devices, but they're not smartly controlled. And then in the bottom part, you have the part of the consumers which are managed by our residential flex platform. So where, in this case, the network operator in combination with the supplier got the right to smartly control their assets. In particularly, we'll look at a specific time period of congestion. So on the next slide, we'll zoom into the purple dashed area. So we look at a single day, in this case, the 1st of June, 2024, around midnight. And before I describe the effects, a quick overview of what the two lines mean. So you have in the light green, we call dispatch. So this is the volume charged, or this is the demand by households. All of this happens in 30-minute increments, so because it's the GB market. So the higher the green line, the more demand by households. And then what you have in blue is what we call the price signal. This is more of an internal term. So in short, this means the signal the supplier sends to the fleet of electric vehicles. And what our platform does is it makes sure the fleet charges when it's cheapest. So by default, this could be spot market prices, day ahead, intraday, any price you like. So you just with this platform, just give it a price signal, and the platform does the rest. It shifts all the volumes within the entire fleet. Just to make it cheapest for everybody, it needs a heads up of a few minutes, but really just a few. And what we then did there is at midnight, our partner told us that they expect large volumes of, or like a relatively congested grid in the area that we were working with. So what our supplier did is they just increased the price signal, so artificially made it more expensive to charge around midnight, which is what you can see in the difference in the blue line when you compare the top and the bottom chart. So again, top one without any changes in any form, and then you'll see a little spike in the blue line in the bottom chart, and then the differences in green. That is what happened as a result of that, and it's what our platform did. So what the platform did, just over the course of these, I think that's 1.5 hours, it just moved all charging basically to either before or after. You cannot move everything to after the point of grid congestion because some consumers need their vehicle charged by a certain point in time. But still, it does that automatically, and all you need to do is just increase that by a few, I'd say euros a kilowatt, or in that case, pounds a kilowatt. Regarding the question in the chat on the price signal, in that case, yes, but our platform offers full flexibility. It can include any monetized signal you like. So this can be spot market prices. This can be network fees. These can be as regional as you want for them to be. This could be taxes, carbon prices, really whatever our, like, let's say you have a trading department, whatever you want to include in the optimization, totally up to you. The only requirement is the price signal has to be expressed in monetary terms. So that is example one. Mainly, so this is from a relatively early point in time. And now we'll talk about a trial that is currently going on the German market. Specifically, this trial is run by one of our partners, Octopus Energy. So brief summary of that, Octopus Energy and Kraken are separate companies. However, Octopus Energy is one of the users of Kraken's flexibility offering. So this is a trial by Transnet BW, so one of the 4 German transmission system operators, and Octopus Energy. And Octopus Energy is running this trial using our software, and they've kindly agreed for us to talk a bit about what they are doing on the German market with residential flexibility. Specifically, what they are trialing is the next generation of the German redispatch system. So for those of you not familiar, redispatch is the German system to alleviate the grid congestion on a technical level. Currently, this is supply side only. So if you are a generator of a certain size, you are required to participate in the system. However, they are currently working towards what they call redispatch 3.0. And by roughly 2030, exact timeline can be debated, they want to allow for flexible demand to participate in this scheme. And this is what Octopus is currently trialing with them. And over the next few slides, I'll walk you briefly through how that works. And all of that will be by flexing the demand of eligible clients of Octopus Energy in Germany. And of course, at the end of the day, the idea would be, let's do that on an entire country basis. So on the next slide, I'll start walking you through a few of the charts. So all of the slides will feature the same chart, and we will then look at how Octopus Energy and Transnet BW work together to alleviate these constraints. So Pete, if you like, just click through until we have 3 lines on there because it's a bit easier. So the way the platform works is, as in the beginning, Kraken's residential flex platform derives the thresholds that the fleet requires to meet consumer requirements. So to give you an example, let's say consumer A or like household A wants their EV at 80% 7 a.m. That's what they tell Octopus. Consumer B doesn't really need it that early in the morning. So they just say, honestly, 9 a.m. works totally fine. All of that gives you, and like the platform makes sure to adhere to all of these requirements. And we're not just talking electric vehicles, we're talking heat pumps and a series of other technologies. So it means there's a certain, like at every point in time, there's a certain bit of charging that you need to do just to meet consumer requirements, which is what gives you the orange and the pink lines. So within your fleet has to charge within this threshold. So this is basically what the flexibility that the trading department has. And then within these boundaries, our flex platform determines the ideal trajectory, which is the blue one. In most cases, this is then based on spot market prices, or as earlier discussed, any price series you want. So this is what Octopus Energy is planning to consume as part of this fleet. And that is then also the nominated baseline they sent to Transnet BW, so the TSO, in that specific region. And now, as the next step, we'll look at what happens when there is grid congestion happening in a certain part of the country. So the way the scheme works is you just one for one ramp one plant down in one part of the country and ramp another one up, or in this case, of course, change demand. So when we look at the nominated baseline, the next thing that happens is the TSO sends an activation signal to Octopus. So that is what the purple line now shows. So in this case, where the purple line drops below the light blue one, this is where the TSO tells Octopus Energy, hey, charge more. Somewhere else, the opposite signal will be sent. And this is a decision by the TSO. Octopus adheres to that. Again, just a few minutes of heads up. And then what happens afterwards is that you'll see now I think light green line is of course in the aftermath. You have to make up for that delta that was previously caused by the activation. So where the green line drops further, this is the redispatch activation. But then of course, at the end of that drop, your electric vehicles are fully charged. So you have to make up for that somewhere else. And this is then what the overall green line gives you. So this is the new signal that the fleet now tries to stick to. Again, overall, same volumes charged. And we then have this signal in light green that is sent to the entire EV fleet. The Kraken Flex platform takes care of breaking that down to what an individual vehicle is supposed to do. And on an aggregate level, the fleet will do just that, or something pretty close to that, which is what we'll look at next. So this is the signal sent to the fleet. And then the next one shows what these vehicles will do in reality, because this is an aggregation of multiple, or hundreds, I think in this example, hundreds of households. We get things pretty close to getting things right. And the bigger the bigger the share of consumers, the better we manage to hit that line. But on, for example, the British market, where our fleet is much bigger, so we're talking, I think, mid 200,000 vehicles, or like either electric vehicles or chargers, we manage to get very, very close to that, and we participate frequently in things like the balancing scheme. And to the best of my knowledge right now, to go back to the German example, this trial is proceeding very, very well. Happy to follow up on when exactly that will be done. But this is just another example of how you don't have to consider the next level or the next generation of demand as a problem. You can think about it as part of the solution. It is technologically complex, yes, but there are solutions out there that are already doing this. And in our view, this will only become more and more useful the more electric vehicles, heat pumps, and whatever you have on the market. And also as technology progresses, and as these technologies will become more flexible. On the new question in the chat, I would have to check. I don't know, Pete, if you know, but I think this will replace Redispatch 2.0. So I think the schemes will replace each other, but you can think in terms of content. I think they'll just add demand as a feature on top. I don't see the Germans excluding, like completely eliminating the certain scheme. I would just assume that demand flexibility will become another option, which might potentially make it cheaper for everybody. But this is my assumption.
That'd be my assumption too. Thanks, Yannick.
Right. With how many slides do I have left? I think 3 if I didn't miscount earlier. Right. So far, that was a lot of theory. I won't give you or not yet give you a tour of the actual software, but a brief sneak peek at what the Kraken Flex software looks like. Happy to do a bit of a live show at the end if we still have time. But this is a screenshot of what we call the fleet overview. So this is from a real client. This is real data. The client kindly agreed to us sharing these aggregate views. So when you take a sneak peek at the platform, it shows you the total number of devices that are currently available. So there's like a few thousand. I think this should be the British market. This is, for now, mainly electric vehicles. There's a few home batteries, and I think there's a single electric charger. The Kraken Flex platform supports a lot more. So you can do electric vehicles, you can do chargers, you can do home batteries, home solar, heat pumps. I hope I didn't forget anything. Or smart thermostats, but I think that is more of a thing in the United States. And then, of course, you can view that growth of your fleet over time, which is if you want to make these models and these tariffs that get residential consumers into the scheme economically viable, you have to make sure, you have to watch how your fleet grows, what the composition of your fleet is, because it also tells you something about how flexible you are with your optimization. On the next one, we'll take a bit of a deep dive into a single vehicle. So let's say you are a supplier, a utility, you name it, that actually has put a tariff in place. So you now have a few consumers who allow you to smartly charge their assets. You of course, want to make sure everything is going well. You might want to check actually what is happening and why. And most importantly, what happens if somebody complains and they say like, well, honestly, we think something on your platform went wrong. We can help you fix that. So what this screen shows you is what we call the charge assessment of the charging performance. So you're actually able to drill down into every single asset managed by our platform. This can be utility scale or residential, and you can check what is happening in minute increment telemetry readings. So what is happening on this one is at the very top, you actually see all of the dispatched volumes. So this is, when is the electric vehicle charging? How does the state of charge change? All of these are interactive. You can zoom in as much as you want. The middle one shows you, just gives you a high level state of the electric vehicle. So particularly the location. I don't know, we don't track electric vehicles down to latitude and longitude. We just track whether they're at home or not, because in our platform, we only optimize vehicles when they are charged at home. So we don't currently, for example, do things like charging at work. And then I think I'll skip the last part because this is more for the technical side. Before we wrap it up, the last slide, just alluding to what I mentioned earlier. So all of this flexing of residential assets, all of these smart devices, making smart devices and the new generation of demand work for grid stability. This is already happening, and it's happening around the world, at least with our platform. So Pete already mentioned this earlier. We currently have a bit more than 2 gigawatts contract capacity, which our clients are allowed to flex. Yes, the majority of that is in Great Britain, but not all of it. And all of the other markets are growing quickly. And at least all of the forecasts I know, they only point up in terms of new and smarter devices coming online. So this is happening. It's happening fast, but it can be a chance instead of a challenge.